Greybus and all. So first an introduction about, so I work with the Linux development team at Texas Instruments. So I primarily work on Linux and U-boot development for Texas Instruments processors. And I'm also the maintainer for TI platforms in the Zephyr RTOS. And also a collaborator for BeagleBot.org platforms in Zephyr RTOS. So coming into the talk, so have any of you heard about Greybus? Do you work with Google? Yeah. So, yes. So, there was a modular smartphone project which was initially started by Google called Project Ara. The concept of that modular smartphone project was that you have a base module of phone, base module, and then you can customize the smartphone to your preference. So if you want a larger, better camera, you want better speakers, you want projectors on the phone, so all those so you want better displays, all those kind of customizations you could achieve through this modular smartphone project. So the concept was that there will be a base module and you will have different modules that you can purchase and add it to your phone, and then your smartphone will be assembled and it will work seamlessly. So there is an underlying subsystem in Linux that was developed as part of this project. The Project Ara smartphone did not make it into the market, but the subsystem or the software development that went into developing the subsystem called Greybus, it is still part of the Linux kernel. So the concept behind Greybus is that you keep all the intelligence inside the host. So you have a base module. So that base module will have the processing entity, and it will be talking to the different modules through a standard protocol. So let's say you have a camera. So you have a camera, you plug in the camera on those. I'm not sure if it's not visible. So there is a slot in there, and you plug that in, and it gets connected to the base module. And there is a standard hardware interface as well as a software interface. So we'll talk into the software interface. You plug the module in. Greybus has its own protocol to discover these modules, what you connected. So let's say you have a camera module. The camera module gets connected to your base module. And so initially there will be a transaction of messages that will be happening between your base module and the camera module. The camera module will be having a microcontroller that runs a generic firmware. So let's say you connected a camera module. So first the host or the base module will ask, what module are you? Then the camera module will respond with something called a manifest telling that it's a camera module and it has these specifications. And on the host is running Android, and it's underlying it's the Linux kernel. So there will be a driver for this corresponding camera, and it will be probed. So all the intelligence is in the host. The host sends messages to these particular smaller modules and makes it do the operation. So in case of a camera, you will tell the module to capture images, transfer images to the host, and different operations. So there's a huge subsystem in Linux that makes possible this modular phone concept possible. But Project Ara did not make it into the market. There was something called motor modes that made it into the market, which also employs the same subsystem in Linux. So to explain simply, so Greybus, you can think of it like a remote procedure call between the base module and the remote module. So here, you are just sending functions to the remote microcontroller or let's say the camera module, and making it do the operations and send back the responses to the host processor. And why Greybus is beautiful is because it has a lot of interactions with the Linux kernel. So now we talked about the smartphone concept. Now think of it as a generic embedded system. So instead of smartphone, you have your, instead of the base module, you have your SoC, or something like a Linux development platform, like a Raspberry Pi or a BeagleBone board. And you have, instead of the add-on module, the camera module, you have a microcontroller which has some peripherals that gets attached to your host processor. So expanding that to an embedded system, what happens with Greybus is that, so in case of, let's say you have a microcontroller, so you have I2C, SPI, GPIO, and all on that microcontroller. And it's connected to the SoC. through let's say the protocol is Greybus. What happens in the background is that, so when we talked about the camera story earlier, so the host will think that the camera is connected directly to the Linux running, the host running Linux will see it as an actual device instead of a plug-on module connected. So in case of an embedded system, what you will see is that this I2C spy GPIO everything appears on the Linux host as if it was actually there, but it's not actually there. It's on another microcontroller, but you get kind of a mirror. So it's very difficult to explain this concept in 15 minutes, so bear with me. So in short, you will see a virtual representation of this particular bus on your Linux host corresponding to a microcontroller. Now, in case of Project Era, you were attaching the module directly to your base module. Now, think of it in a wireless IoT system. So you are not connecting it directly. You have a Linux host, you have a microcontroller running Greybus, and on this Linux host, the peripherals on this microcontroller appears as if it was directly on the host. So what happens is, if you are familiar with Linux, Linux has something called a sysfs file system where you can explore and do operations on devices on the system. So if you look at this, so you see an I2C 8 device, but that's actually not. So this was captured from my laptop, but that bus is not actually on my laptop. It's on a remote microcontroller sitting far away from the laptop. How it came as a standard Linux interface is through the Greybus protocol. And Greybus covers a lot of protocols that it's apt for a lot of embedded use cases. And now coming to the role of Zephyr. So Zephyr, I think of Zephyr like a Linux for microcontrollers. So it has Linux-like architecture, different APIs, and a device tree system, which makes development a lot of easier. When the Project Era project was introduced, originally the Greybus firmware was written in an RTOS called NutX. There was an effort with BeagleConnect and some maintainers from Zephyr RTOS, and we ported this to Zephyr RTOS. And the benefit is that most of the RTOS you look at, let's take free RTOS or NutX or different RTOS, so the platform code and the actual logic is not decoupled. So if you look at, let's say you have different hardware instances, it usually goes into the code. But in case of Zephyr, the device description and the platform description stays in the device tree, and an application layer protocol like Greybus, if you implement it in Zephyr, multiple platforms can make use of it by just adding the device tree descriptions for that platforms. So I mentioned that a remote peripheral will appear on your Linux machine as if it was actually there. So what happens when I toggle a GPIO? Let's say there is a remote microcontroller that has a GPIO that connected to LED. So and a Linux machine. So I use a standard Linux command called GPIO set, which is tied with the Linux GPIO subsystem. I try to set the GPIO. What happens is it goes to the GPIO subsystem in Linux, then the Greybus GPIO driver is implemented, and it goes to the subsystem, and it packs into a message telling that you have to toggle the GPIO. Then it sends over some transport. In our case, it was sub-gigahertz low-pan network, and so this message is sent to the Zephyr node. All the functions that happens in the right is the Zephyr implementation. So that implementation is also generic. So you get a TCP/IP packet, you decode the message, and you will have different handlers for different functions, and the GPIO set value will happen. So through this sequence of operations, something similar like a GPIO toggle happens. But the beauty of using Zephyr for embedded systems is that you have implementations for multiple subsystems, I2C, everything, and you take it to the next level. Let's say you have implementation for I2C. Then there is a device on the Zephyr node that has a Linux kernel driver in Linux. So you can attach Linux kernel drivers to devices attached to your microcontroller. So virtually you are not doing any low-level development. So I have a demo showing what's happening with the Greybus running for IoT with Zephyr. So before the demo, I just want to introduce you to a few hardware that's getting used in the demo. So uh, this is a BeagleConnect Freedom Development Board. It's a wireless microcontroller development board from beagleboard.org. It features a Texas Instruments wireless processor and uh, something called microbus add-on connectors, where you can plug in different add-on cards like this and expand your system. So, and you have something called a Beagle Player Gateway that runs Linux. So in the previous Project RS modular smartphone story, the gateway running Linux is your base module, and the BeagleConnect, the remote microcontroller development um, platform is the modules that gets attached to your smartphone. And instead of physical attachment, it's a wireless network. So in this demo, what I have here is, I only have the host side of the things. Not sure if it's very visible. So what I have here is, you saw the previous Linux gateway, and I have a microcontroller connected with some modules kept apart. So I start the gateway application. So it performs the remote setup. So it detects that a device is there. It pings the remote device. Now I am so now the gateway is propped. So what happened is, so during this process, this module told the host that this is a BeagleConnect Freedom running Zephyr. It has a humidity sensor, it has a light sensor, and the name of the light sensor is OPT301, which has a Linux kernel driver, and the name of the humidity sensor is HDC2010, which also has a Linux driver. Now what happens is, the Linux host, now in the Linux host, these two sensors appears as it was actually directly connected there. So if I was running on the laptop, I'll see a temperature sensor and a light sensor on my laptop. I will use standard API. So I'm using something called IIO info to display the sensor values from this device. So what happened here was, I did not even know what sensor I connected to this board. So from the Linux kernel, the open source drivers, all the development that has gone in the past, I was able to reuse that work to get readings from the this sensor. And we have tested close to 150 devices, 150 add-on boards. So like you're looking at the Project Arab smart modules. So you have close to, you pick another module and plug it into your BeagleConnect Freedom, you have another module to expand it to. And you don't need to do any low-level development. And not part of this talk, but there is also a new technology that this add-on card vendor has added, where these add-on cards are also self-identifying. So you plug it in and you get a plug-and-play support. Like you plug in your USB keyboard, you don't write drivers, you don't probe drivers, and you don't describe it. So that kind of comfort is what BeagleBoard, the investments in Zephyr RTOS and the BeagleConnect Freedom technology is bringing in. Yeah. Okay, any questions? So